See guys, I am going to start with the revision of metal casting chapter. Today we are going to see the total 4 chapters. First is metal casting, second is welding, third is advanced machining method, and fourth one is non-traditional machining method. Then I am starting with here the metal casting here. Today we have to do the revision of here metal casting chapter. Guys, when we are going to start the metal casting here, then you can see firstly we are going to discuss about the shrinkage. That is the two type of shrinkage are there, that is the liquid shrinkage and solid shrinkage, and for that I am drawing this graph. Yes, now here you can see that there is one graph. Here you can see this is one of the graph. On the x-axis there is the time, and on the y-axis you can see there is the temperature. On the x-axis time and y-axis there is the temperature. Guys, we are going to pour the molten metal at this temperature, and that temperature I am writing the TP, pouring temperature. This I am writing the TF, freezing temperature, and finally this I am writing the TR, that is the room temperature. Means there are the two type of shrinkage. This is very big question. Then what is the liquid shrinkage is here? Guys, we are going to pour the molten metal at the pouring temperature. When we are pouring the molten metal, then you can see that from this point, I am writing here the point A here. This is the point A, this is the point B, this is the point C, and this is the point D. Then you can see that A to B, the liquid shrinkage is there. Means we are pouring the molten metal at the temperature at point A, then it is going to cool from A to B. It is going to cool from A to B. Okay, then this is known as here the cooling is going on. At A point the temperature is pouring temperature, and at B point the temperature is freezing temperature. Now guys, some student they are facing the difference between the what is the melting point temperature and what is the freezing temperature. Both the temperatures are remain same, but melting temperature means when we are converting solid into liquid, it means that when we are giving the heat, when we are supplying the heat, that is known as melting temperature. And when we are using the freezing temperature, when we are going to cool the molten metal, when we are converting the liquid into solid, at that point we are using the temperature here, and that is the freezing temperature. Both the temperature are remain same, but the reverse condition is there, right? Then guys, at A you can see the liquid is there, at B also the liquid is there, but B to C the liquid is converting into solid. B to C the liquid is converting into solid. Now here you can see that A to B liquid remains liquid, but the temperature is going to reduce, and B to C is what happened, the liquid is converting into solid. Then where the liquid shrinkage is there, means where the liquid is converting into solid, then in the stage 1, this is the stage 1 A to B, and B to C is the stage 2, means in the stage 1 and stage 2 the liquid is there is shrinkage of liquid, therefore it is known as liquid shrinkage. Therefore, it is known as liquid shrinkage. And what about the solid shrinkage, guys? You can see from point C to D there is a solid shrinkage. C to D there is a solid shrinkage, because at point C there is solid, and at point D also there is a solid. Okay, then it is known as what? Solid shrinkage. Solid shrinkage it is known as. Then guys, here we have to write down the formula for solid shrinkage here. Okay, then guys, solid shrinkage means solid remains solid, but something is going to change. The temperature of that component is going to reduce from C to D. Then what about the size of that component? Is the size of that component is going to reduce? That we have to discuss here. Okay, that we have to discuss here, and therefore here I am writing the solid shrinkage. Solid shrinkage. Yes. Okay, solid shrinkage means, in the solid shrinkage means what, here we have to see the what is the shrinkage is there, means I can say that what is the change in length is there, and it is denoted by delta L, and it is denoted by delta L. Then I am writing here change in length, change in length, and it is denoted by delta L, and that, guys, the delta L is equal to, I can write the L minus L dash. L minus L dash. Now there is a big question, what is L minus L dash? Now see, there is one cubical component, just consider. You can see this component has this dimension here at point C, and after at point D it got the final dimension, this one. This is the cubical component, you can see. Then what are the dimensions at point C? Here you can see that this is at point C. I am writing here the C point is here, and this is the final condition, this point is, D point is here. Then, guys, when it was the C point, then I can write here the length was capital L, okay, and then the length is going to change, and it is the L dash, and it is known as change in length, or also we can say that solid shrinkage. Then when you are doing the casting physically, then you can measure the length at point C. How you can measure the length at point C? Guys, you are going to break the mold at point C only. Means when the liquid is converting into solid, then you are going to break the mold, and at C point the liquid is converting into solid. At C point we can get the perfect solid, and at that point we are going to break that mold. Then we can measure the length of component at point C, and then C to D there is some shrinkage is there, there is some reduction. Here you can see that some reduction in dimensions are there. The reduction in dimensions are there, you can see the reduction in dimensions are there, you can see. And it is the same formula, thermal stresses in the strength of material subject, and same formula also we can use here. Then I am using the formula here, change in length is equal to alpha delta TL. Then here the alpha, what is the delta T, guys? From where to where the solid shrinkage is going to happen? The solid shrinkage is going to happen from point C to D. At C the temperature, you can see that the freezing temperature. At a D you can see the temperature is room temperature into capital L. Then, guys, here the number of parameters are available. Then what is the alpha? Alpha is what? Coefficient of thermal expansion. Alpha is coefficient of thermal expansion. TF is freezing temperature, guys. TR is room temperature. L is initial length of component, or here we can see that the length of component at point C, or also we can see the initial length of component, or also we can see the initial length of component. Initial length of component we can say. Initial length of component. Okay. Initial length of component. Okay. This is the formula about the, guys, solid shrinkage. Okay. And that formula is also asked in number of exams. That is, but in old exam, GATE PI once and GATE mechanical once, they asked a question on this formula, some theory question they asked on this formula. Okay, this is the first topic here which I have to revise, and that is the solid shrinkage. Okay, guys, next we have to see here the permeability number. Next we have to see here the permeability number. Okay. Permeability number. Permeability number is the next topic here. Permeability number. Guys, the permeability number means we are going to denote by Pn, that is the permeability number, and it has the wonderful formula here, VH by PAT. VH by PAT. Now here the question, guys, what is the capital V? Capital V is what? Here the volume of, here capital V is the volume of air. And what the volume of air we are going to supply here? 2000 centimeter cube. Okay, guys, if you already studied the casting chapter, then it is easy for you. If you didn't studied, then here very difficult to get the number of points here. Okay, then here the VH by PAT, guys, there is one specimen. I am now drawing the diagram of that specimen, and in that specimen we are going to supply the volume of air, and that volume of air is 2000 centimeter cube. Then capital V is what? Volume of air. Volume of air, and guys, its value is 2000 centimeter cube. 2000 centimeter cube. Okay, means guys, to that specimen we are going to supply the 2000 centimeter cube of air. We are going to supply. And then here you can see the capital H, guys, the height of specimen. You can see height of specimen. Height of specimen. Now, what is mean by specimen? Guys, we are mixing some sand particles. We are taking some sand. In that sand, we are mixing some clay. We are mixing some water. We are mixing some wood powder, coal powder. We are going to add into that, and we are going to make one specimen. And this H is the height of specimen, guys. And guys, what is the height of specimen? Here, the height and diameter of specimen is remains same. Here, the height and diameter of specimen is remains same, and we are saying as the height is 2 inch. But guys, in the calculation, we are not taking in inch, we are taking in 5 centimeter. That is the 2 inch is equal to 5.08 centimeter. Okay, we are taking the calculation in centimeter. Here you can see that the volume of air is 2000 centimeter cube. Here also you can see that it is a centimeter. You see here also it is centimeter, 5.08. That is the capital H is what? The height of specimen here. Capital H is height of specimen. Okay, then guys, what is the here capital P? Capital P means what? The pressure of air in the specimen. Then I am writing here the pressure of air. If guys the pressure of air is not given, then what the pressure we can consider? Okay, they need to mention that pressure, guys. They need to mention that pressure in the numerical. The most of the time they are going to mention the 5 gram per centimeter square. Sometime also they are going to tell 10 gram per centimeter square. But generally, if it is not mentioned, then we have to take the 10 gram per centimeter square. You can see the unit, the pressure we are going to measure in gram per centimeter square, guys. Okay. Then this is the pressure. Then what is capital A? Cross-sectional area of specimen. Cross-sectional area of a specimen here. Cross-sectional area of specimen. Cross-sectional area of specimen. Guys, what is the cross-sectional area of specimen? The circular specimen we are going to use, and circular specimen means cross-sectional area is circular and it has some height. Means cylindrical specimen we are going to use, and here the cross-sectional area it is, that is the pi by 4 into d square. But guys, here we written the H is equal to height of specimen, it is 2 inch, that is 5.08, and here guys we are using the height and diameter remain same. Okay. Then next is guys the capital T here. Yes, capital T. Guys, whenever we are using the capital T, then always we have habit to take in seconds. But here guys, the capital T, always we have to take in minutes. This T we have to take in minutes. Never take in second. If you are using the second in this formula, definitely you will give the wrong answer. Then what is the capital T? Okay, what is the capital T, guys? It is the time required or time taken by air to pass through. Time taken by air to pass through sand specimen. and I need to write here in minute. Okay, then you must take, guys, that time is in minute. Okay, then guys, here now we need to put the number of values here in the permeability number formula. Then here in the permeability number, I am writing the Pn permeability number is Vh by PAT. V is 2000, H is 5.08, pressure only P I am taking. Area is what? Pi by 4 into diameter square. Diameter and height is equal into T. Okay, if we are going to calculate, then you will get 501.28 divided by PT. But guys, most of the time the P pressure, if not given in the example directly, you can take the 10 gram per centimeter square. Therefore, the permeability number here I am going to put the pressure as 10 into 10 gram per centimeter square. Therefore, here you can get the final answer, that is 50.128 divided by T. This is your final formula for permeability number. Guys, permeability number doesn't has any derivation, guys. No derivation for permeability number. No one is developed derivation for permeability number. Therefore, it is not a derived quantity. It is not a derived quantity. It means that it doesn't has any dimension. It is permeability number is number only. No any dimension. Only number is there. It is some empirical relation developed by AFS, guys. It is developed by AFS. What is mean by AFS? It is developed by American Foundry Society standard. American Foundry Society developed this relation. It is some empirical relation. Okay, they taken one specimen, they made one specimen, and guys, that all the dimensions are fixed. The volume of specimen is fixed. Height is also fixed. Okay, height is fixed, then cross sectional area pi by 4 d square, that value is also fixed. The two values are not fixed here, pressure and time. Here the two values are not fixed here. Why the two values are not fixed here? If you studied well the casting, then you know that if you are going to add the wood powder, then permeability is going to increase. If you are providing the vent holes, but don't worry about the vent holes here. If we are going to put the or going to increase the quantity of wood powder, then the permeability is going to increase. If the permeability is going to increase, then what happen? When we are passing the air through the specimen, then here you can see that the pressure, here you can see that the value of pressure will be less. Here the value of pressure will be less. Okay, and what is the capital T here? Time taken by air to pass through sand specimen, and air will go out very easily, then the time is also going to change here. Pressure is also less, pressure will be there, pressure of air will be less here, and time will be less. Both quantities are less, therefore the permeability number is going to increase. And if the permeability number is going to increase, then definitely it is good, it has good porosity, we can say that. Guys, the porosity we are going to indicate in terms of permeability number. Porosity is indicated in terms of permeability number. In terms of permeability number. Then to check the porosity, guys, okay, we are using the permeability number. Okay, guys, this was the second topic here for the revision, and now the next topic is buoyancy force, guys. Buoyancy force. Yes, now the buoyancy force, guys, but here we have to calculate the net buoyancy force. What is meant by net buoyancy force? Shall I draw here the diagram? Just see, I need to draw here one diagram. This is very confusing point for the number of students. Yes, guys, here we are going to fit a core here. Here we are going to fit one core here. Okay. Now listen carefully. This core has some weight, and that weight is always going to act in the downward direction. This is the, I am writing the WC, that is the weight of core. And guys, when we are pouring the molten metal, now see, this is one of the core, this pane is the core, and the molten metal from front side as well as back side will enter into the cavity, and casting cavity will be full of molten metal. And when that molten metal will touch to that core, then it is started giving the net upward forces. Okay, it is started giving the net upward forces. Okay, and that forces are known as buoyant forces. And here I am writing the buoyant force, or also I can write the weight of molten metal, or buoyant force. I can write the buoyant force. BF is the buoyant force, we can write it here. Okay, we can write here the buoyant force. It is in upward direction, right? And that buoyant force, if you learn the fluid mechanics subject, then guys, that buoyant force is also known as weight of molten metal passed. Then here guys, we have to calculate the net buoyancy force. Here we have to calculate the net buoyancy force, we have to calculate. Just see, very interesting concept, net buoyancy force. Net buoyancy force. Guys, here the net buoyancy force means what here? Net buoyancy force means, you can see that buoyant force is going to act in the upward direction. The buoyant force is going to act in upward direction, and weight of core is going to act in the downward direction. Just consider that if the buoyant force is 10 Newton, the upward direction, and weight of core is 7 Newton, then what is the answer? Answer is 3 Newton is the difference, and it is known as net buoyant force. Because even though the buoyant force of 10 Newton is going to act in the upward direction, the 7 Newton is going to act in downward direction, then what is the net force here? Only the net force is 3 Newton, and it is known as net buoyant force or net buoyancy force, or also we can say that the net upward force here. Then here I am writing the net buoyancy force is equal to weight of molten metal displaced minus weight of core. Okay. Then here the net buoyant force is equal to weight of molten metal displaced minus weight of core. Then weight of molten metal displaced means here the BF, that is the buoyant force or buoyancy force, minus weight of core. Then guys, weight of what is the weight of molten metal displaced? That is only the buoyancy force. Fluid mechanics, Archimedes principle, the buoyancy and flotation is the name of that chapter. Then here the buoyant force or weight of molten metal formula is rho g H. This formula is rho g H for molten metal minus here rho g H for core. Okay. Then here guys, I can take the area into height is what? The volume. Then it is the volume of core guys, and here what? Area into H, volume of molten metal displaced, and This is AH is what? Volume of core. Now guys, here the volume of core means from here to here we can take the volume of core. Here volume of core we can take. Okay. Then guys, just take one example. There is one bucket of water. In that bucket of water I inserted my hand. Then what is the volume of my hand? Same volume of molten metal is displaced. What is the volume of my hand? Same volume of water is displaced there. In the same case, what is the volume? Means total volume we are not considering. The small volume we are going to neglect it here. The small volume we are going to neglect it here. Only we are considering from this point to this point, this volume only we are considering. This volume we are considering. The remaining volume of core we are going to neglect because it is very small. Then here rho g AH, A into H is what? The volume of molten metal displaced. Here what is the volume of core? Same volume of molten metal displaced. Therefore, I am taking here the volume common. Into G also I am taking common, and here I am writing the rho m minus rho c, guys. Here I am writing rho m minus rho c. Okay. Then this is the formula for net binds force, net bind force. This is the formula for net bind force. Or again, in here this formula I written in the form of rho density. Then here you can see that this volume I am writing, I am again multiplying by G to the bracket, then G into rho m minus G into rho c. Then here it is the gamma, guys. Here it is the gamma. Here it is the gamma. Okay, gamma is equal to what? Rho into G. Gamma is equal to what? Rho into G. Okay, what is the gamma? Gamma is the specific weight, we can say, or weight density. Therefore, here the formula for net buoyancy force is equal to volume into gamma m minus gamma c. Okay, this is also one of the formula. The two formula we have, this formula in the form of density and this formula is in the terms of gamma, right? Then guys, all I need to write here, what is the rho m? Rho m is density of molten metal, rho c is the density of core. Rho m, density of molten metal, rho c, density of core, gamma is specific weight, or also we can say as weight density. Okay, then guys, what is the unit for density? Unit for density is kilogram per meter cube, and here specific weight is Newton per meter cube. Okay, specific weight or weight density as a unit Newton per meter cube. Then next is capital V here. This is the volume of core, or also we can say that volume of molten metal displaced. Volume of molten metal displaced. And here you can see, here we written the formula for net buoyancy force, or also we can say that net upward force. Net upward. Net buoyancy force, or also we can write as net upward force. Net upward force. Okay, understood, guys? Net upward force. Okay, net upward force. This is the formula. This is somewhat difficult topic to understand how it is going to happen. Yeah. Now guys, the next topic we have to start with the powering time here. Powering time. Powering time. This guys, what time is required to pour the molten metal, that is known as powering time, or also we can say that the powering time or also we can say that the filling time. Then what is the pouring time or filling time? Filling time is what time is required to fill the molten metal in casting cavity. Or what is the pouring time? What time is required to pour the molten metal in the casting cavity? So both the time is same, we are saying as the pouring time or filling time. Guys, you know that we are pouring the molten metal at the pouring temperature. And what is the pouring temperature? Here, if the metal casting chapter is there, in the chapter, we taken one example in the our theory lectures, for iron material, the melting point temperature is 1539, but we are giving some extra temperature, and that is known as degree of superheat. And the degree of superheat is 150 degrees centigrade to 200 degrees centigrade is the degree of superheat, and therefore we are going to pour the molten metal at a temperature 1700 degrees centigrade we are pouring. Then guys, we are pouring, but what time is required to pour the molten metal, that is also important for us. Then that pouring time formula is volume divided by flow rate. Volume divided by flow rate. Volume divided by flow rate. Then is equal to volume here. Flow rate means area into velocity. Here I can write the minimum area and here velocity maximum. Okay. Then guys, here in this formula there is big question, volume means whose volume? You tell me, volume means whose volume, guys? Here the volume is volume of casting cavity. This volume is what? The volume of casting cavity. Okay. Or also guys, in the some numerical you can see that is the volume of casted component is given. Means if the volume of casted component is given, then you need to take the volume of casted component. Okay, this is not a volume of pouring basin. You need to remember that this is not a volume of pouring basin. Okay, this is not a volume of pouring basin. Then guys, volume of casting cavity, or in the numerical directly they are giving the volume of casted component, that we have to use it here, divided by area minimum into V max. Then minimum area is, which is the minimum area? Guys, the minimum area means either it is the area of a sprue or area of runner or area of ingot. But guys, out of that, which area we have to take? Guys, the minimum area we have to take. Means I can write the minimum of either area of a sprue or area of runner or area of ingot. We have to take any area which is minimum. Means it is area of sprue, means it is a cross sectional area of sprue. The sprue has the two cross sectional area, one is at the top and second is at the bottom. Always we are taking the bottom cross sectional area. And either it is area of sprue, runner, ingot, which is the minimum, that minimum we have to take. And here the velocity max, you can see that. Here what is the velocity max is equal to into 2gh total. Means total height, or also we can write the height of sprue, or the total height means height of pouring, also we can write that. Okay. Then guys, here what the pouring time we require? The pouring time must be high or pouring time must be low. Pouring time must be low means in the minimum time we are going to pour the molten metal, and that is always better. In the minimum time we have to pour the molten metal. In the minimum time we have to pour the molten metal, and therefore guys, the velocity of molten metal must be higher. Velocity of molten metal must be higher. If the velocity is high, then definitely here the pouring time will be low. If the velocity is high, then definitely the pouring time is low. Here guys, we cannot change that area. Here this area we cannot change. Here that area we cannot change, guys. Why the area we cannot change? because when we are going to manufacture, we are going to make the mold and we are going to fix the bottom area of sprue, then the area of runner cross sectional we are going to fix, therefore we are not changing that terms. But guys, the velocity we can increase. If the velocity we are going to increase, then pouring time is going to reduce. And guys, also this velocity is depend on some terms here. Velocity is also depend on some terms. Okay. Then guys, the velocity is depend on what? Velocity is depend on viscosity. Viscosity of molten metal. And if guys, the temperature we are going to increase, if the temperature of molten metal we are going to increase, then viscosity is going to reduce. If the viscosity is going to reduce, then velocity is going to increase. Then velocity is going to increase here. Then velocity of molten metal is going to increase here. Okay. When we have to increase the temperature of molten metal, means if we are going to increase the degree of superheat, we are going to increase, then viscosity is going to reduce. Viscosity is going to reduce. Viscosity is not increasing. Viscosity is increasing means fluid is thicker fluid. Viscosity is going to reduce means it is the thinner fluid. And as the temperature is going to increase, the distance between the number of molten metal molecules is going to increase and the viscosity is going to reduce. Viscosity is going to reducing, viscosity is going to reduce means the molten metal can spread over the surface very easily and then the velocity is going to increase. Means guys, it is when the velocity is going to increase, then pouring time will be less and always we want that. Always we want that in the pouring time. The velocity of molten metal must be higher and therefore we can pour in the minimum time. But guys, the velocity must be higher, but within the limits of laminar flow. Now, what is that new term laminar flow? Guys, here one formula for Reynolds number I am writing. The Reynolds number is rho Vd divided by mu. Then here, as the velocity is going to increase, Reynolds number is also going to increase. And if the value of Reynolds number is up to 2000, then it is laminar flow, it is better. But when it is going to enter into the turbulent flow, 2000 to 4000 is the transition, but if it is going to increase more than 4000, then turbulent is there. And because of turbulent, what happens when the molten metal is flowing through the gating system? What is meant by gating system now? Pouring basin, sprue, runner, ingate is known as gating system. Then forces are more in the gating system because of turbulent flow, and because of forces the erosion of sand may be there, and therefore we need to avoid the turbulence. Therefore velocity must be higher, but within the limits of laminar flow. Okay guys, yeah, and that is the enough discussion about the pouring time. Yes. Now next is here solidification time. Solidification time. Okay, solidification time. Now guys, what is here the solidification time? Now see this diagram here. Is anyone can tell the solidification time definition? Yes, this time is known as solidification time. Means here you can see that here the pouring temperature is there and here the freezing temperature, but here the liquid, here the liquid, here the solid. Means this tau is known as what? The solidification time. Understood? Please. Yes. Now in the solidification time you can see the formula here. Tau is directly proportional to the modulus square, then tau is equal to K1 into m square, and this is known as Shorino's equation or Shorino's rule also we can say that. Okay, then tau is equal to, tau is what the solidification time is there, and you know this is the solidification time here, okay, which I written. Then here the tau is equal to K1 into m square, then tau, you know what is the K1 here guys? K1 is Here I can write the constant, the K1 is constant, and which is known as solidification constant, which is known as solidification constant. Then here you can see the capital M is known as modulus, and that modulus is, I am saying, mold modulus. It is known as mold modulus, okay. Or also guys, the simple, not only mold modulus, we are also saying that only modulus also we are going to use the word, okay. And K1 is solidification constant, or also we can say the mold constant, okay. And this is what capital M is, what modulus, capital M is modulus, you need to use the word, but here the modulus for mold we are going to see. There is one topic riser, then we are going to see the modulus for riser. Here we are going to see the modulus for mold, therefore it is mold modulus. And guys, here the formula for mold modulus is also there. Mold modulus is equal to what? Volume divided by surface area here. Then again, whose volume is that? This is the volume of casting cavity, and AS is what? The surface area of casting cavity losing heat. Yes, what I am saying. Capital V is the volume of casting, capital V is the volume of casting, capital V is the volume of casting. And what is the capital AS? What is the capital AS? Just see, volume of casting, or also I can write the volume of casting cavity. There is not a big difference between the volume of casting and volume of casting cavity, and AS is surface area of casting, surface area of casting losing heat. Means guys, what happen in one of the question, they can tell that one component is there. Just see the cylindrical casted component they given, and they can mention that the top surface is not transferring heat. The top surface of that cylindrical casting is not transferring heat. And what is the surface area in that case? Surface area of casting losing heat, top surface is not losing heat. Then the curved surface of that cylindrical component and only the bottom surface is transferring heat, then only that two surfaces we have to take. Okay, it is very important guys, it is very important. Okay, I hope so you solved the number of numericals and you understood how it is going to happen. Okay, surface area of casting losing heat. If the cylindrical component, if they are saying the curved area is not transferring heat, then what is the surface area of casting losing heat? Only the top and bottom of cylinder. The top of cylinder is pi by 4 d square, the bottom of cylinder is pi by 4 d square, addition is 2 into pi by 4 d square, that is the surface area we have to take. When the AS is going to come, the people are saying that the surface area, no, it is not only surface area, it is a surface area of casting losing heat. Okay, it is very guys important to remember that. Okay, this is the formula for solidification time. Guys, the number of numericals are available on the solidification time. Okay, now guys, we have to go with the next wonderful topic here, the riser design. Riser design, or also we are saying as the feeder design. Or for that riser is feeding the molten metal, therefore we are also saying that the feeder design, it is feeding the molten metal, means it is supplying the molten metal, therefore it is also known as feeder design. Okay, riser design. Guys, what is mean by design of riser? Or you know the machine design subject, then we are designing something, we are calculating some dimensions here, and therefore guys, we have to calculate here the dimensions of riser. Then the question, we have to calculate the dimension of riser. Then the question, the riser is cylindrical in shape, cubical in shape, rectangular in shape, spherical in shape, hemispherical in shape. What type of shape the riser have? This is a very big question. And guys, firstly we have to discuss about the shape of riser, then we can calculate the dimensions of riser, and therefore the name of topic is what? The riser design is the name of topic. Okay, guys, here we are using the cylindrical riser. We are using the cylindrical riser, guys. We can use the cubical riser also. We can use the spherical riser also. We can use the cylindrical riser also. But guys, when we are going to develop the riser, what is the use of riser? What is the use of riser, guys? Guys, here we discuss the number of stages. Here you can see that in this diagram also you can see here is the liquid to liquid. Here the temperature is going to reduce. This is the stage 1. This is the stage 2. Liquid is converting into solid. Guys, in the stage 1 and stage 2, in the both stage, guys, what happen? The liquid shrinkage is going to happen. In the both stage, what is going to happen? Liquid shrinkage is going to happen. Means shrinkage of liquid is going to happen. The volume of that liquid is going to reduce. Volume of that liquid is going to reduce, guys. Okay, the volume of that liquid is going to reduce, guys. And guys, if the volume of liquid is going to reduce, then what happen? We need to supply some liquid there. We need to give some liquid there. Otherwise, underside the component can be produced, and therefore we have to learn the riser design for that purpose. Why I am telling that? Why I am telling that in the revision? Because guys, the riser is going to compensate the liquid shrinkage. It is very important. Riser is going to compensate the liquid shrinkage. Riser is going to compensate the liquid shrinkage. What is mean by compensate? Means whatever the liquid shrinkage is going to happen, same quantity of molten metal the riser is going to supply, and therefore we are saying that it is compensating. It is going to compensate. Means what is the liquid shrinkage is here? The same quantity of molten metal supplied by riser. The same quantity of molten metal supplied by riser. The same quantity of molten metal supplied by riser. Therefore, in the stage 1 and stage 2, the volume of that casted component is not going to change. What is the shrinkage of liquid? Same molten metal, same volume of molten metal supplied by riser. Just consider that if 100 millimeter cube molten metal we poured into the casting cavity. Guys, the shrinkage is 7 millimeter cube. Okay, then riser is going to supply same 7 millimeter cube molten metal. Correct? Therefore, we are going to maintain here 100 millimeter cube of volume. Then this 100 millimeter cube means we are saying that the volume of casting and 7 millimeter cube is the shrinkage. Therefore, we are saying at the shrinkage volume here. Shrinkage volume is 7 millimeter cube. Okay. Now guys, here which type of riser, which shape of riser we have to use? Guys, we have to use the riser such that whose surface area is minimum. Or also we can say that the surface area for heat transfer must be minimum. Surface area for heat transfer must be minimum. It means that if the surface area for heat transfer is more, than what happen? Through the riser, more heat loss is there and riser will convert into solid. But here guys, the casting must convert into solid first, and after then riser need to convert into solid. If the riser is converted into solid first and after then the casting is converting into solid, then when there is a liquid shrinkage is there, then how that riser can supply the molten metal? How that riser can supply the molten metal? Riser cannot supply the molten metal, because in the riser what is the molten metal was there, now it is not a molten metal, now it is the solid metal, it cannot supply. Therefore guys, we have to select such a riser that, we have to select such a shape of riser that whose surface area is minimum, and therefore we have the three options. One is cubical riser, one is cylindrical riser, one is spherical riser. Guys, the spherical riser has lowest surface area for heat transfer, therefore we taken as the best option as a spherical riser. But it is very difficult to make the spear like shape inside the cope. Inside the cope, the top portion is cope, or inside the mold we can see that inside we need to break that. Inside, from inside we need to break that and we need to make the spear. It is difficult guys, it is not that easy. Therefore, we taken the best riser as cylindrical riser, and guys, in the cylindrical riser there are two type of cylindrical riser is there. One is top riser and second is side riser. Then what are the diagram you are going to see? This is the diagram for guys the top riser. Therefore, here I am writing the top riser. Therefore, here I am writing top riser. Okay. Here this is the top riser. This is the diagram of top riser. Okay. And next is the diagram for side riser I am drawing here. Yeah, the two type of diagram of side riser I can show it here. One is for solving the numericals. Guys, for solving the numericals I am drawing the diagram like that. This is the side riser for solving the numerical. But when the actual case is going to happen, means actually when we are doing the casting, then you can see the diagram of side riser is like that in the actual casting. Understood? Now here you can see that here both the diagram is for side riser. For solving numericals or calculation we are using this case, but actual, or I can say the practical, this case is there. This is the side riser here, this is the side riser. And guys, when in the numerical, they are not mentioning in the numerical whether to use the side riser or top riser. Okay, they are not mentioning whether to use the side or top riser, or they are not giving any clue also which riser is there, then always go with the side riser and why so. There was one question in the GATE PI exam 2019, the same type of diagram they given in that question. Then we have to consider the side riser only. Now why it so? Guys, when we are using the side riser, just see we have started the pouring molten metal here. Now here you can see that the molten metal is entering here into the riser. Means first you can see that the casting cavity is going to fill, then this runner is going to fill, and then the molten metal is entering into the riser. Means at the end, the molten metal is entering into the riser. Therefore, the hottest molten metal is going to enter into the riser. Therefore, the hottest molten metal is going to enter into the riser, and the more time the liquid can be maintained. But here in that case, you can see that when the molten metal is entering, directly that molten metal is entering into the cavity, and when the fresh molten metal is entering, it is entering into the cavity, and cold means the total molten metal, what is going to collect in the cavity is going to enter into the riser, here. Okay, is going to enter into the riser. Okay. Therefore, the cold molten metal here entering into the riser, but here in the side riser, the hottest molten metal is going to enter. Therefore, always go with the side riser. Okay. If nothing is mentioned, then you can go with the side riser. Okay. Yeah. Now, one important topic is there. The number of time we already studied some derivation of top riser and side riser we have to see. Why the derivation we have to see? Through that derivation we can get the dimensions of diameter and height, and depend on that we have the number of methods of riser design. The total 4 methods of riser design are there. Now, here we can see the top riser. What is meant by top riser? The riser is placed at the top of casting cavity is known as top riser. Riser is placed at the top of casting cavity is known as top riser. Already you know the diagram of here. This is the diagram of top riser. Then guys, here the question, what is the volume of riser here? What is volume of riser? Here guys, either it is a top or side riser. I said that the cylindrical riser we are going to use. Then what is the volume of cylindrical riser? It is the pi by 4 d square h. D is the diameter of cylinder and h is the height of cylinder. If someone want to show it here, then we can show that this is the height and this is the diameter. Okay, this is the height and this is the diameter. Then here the volume is pi by 4 d square h. Then here it is h is equal to 4v divided by pi d square, 4v divided by pi d square, that is a hv taken. Okay. Now guys, here the surface area exposed to heat transfer, we have to write the surface area. I am writing here yes, surface area exposed to heat transfer, surface area exposed to heat transfer. Then what is here the surface area exposed to heat transfer? Now guys, here you can see that the top surface is transferring heat and these vertical lines you can see that that vertical lines are the curved lines, that curved lines are also transferring heat, that area only we have to take. Then guys, the top area transferring heat, that is pi by 4 d square, and curved area means I can write here the pi dh. Top area means circle, you can see that is pi by 4 d square and curved is pi dh. You can see the bottom area is not transferring heat because at the bottom you can see the molten metal is there. Okay, then here the pi by 4 d square at the top, then I am writing here the pi by 4 d square plus, guys, here na h is there and guys, I need to convert that surface area in the terms of d. In the terms of d I want to convert, therefore pi by 4 d square plus here I am writing pi d. H is what? 4v divided by pi d square. Okay, 4v here divided by pi d square. Okay, then guys, here you can see that these pi get cancelled, these get cancelled, therefore we can write here the 4v divided by d. Therefore here surface area is equal to pi by 4 d square plus 4v divided by capital D. Now guys, this surface area we got in the terms of d, there is no h, h is the height of that riser. Therefore guys, for minimum surface area, means we want minimum surface area. Tell me why we want minimum surface area. We can take here this derivative of surface area with respect to capital D is equal to 0. Derivative of this surface area with respect to capital D, because this surface area is in the terms of D only, it is not in the terms of H. If here we are taking d square or d is equal to something root, then this whole equation will be in the terms of H. Then we can take the derivative of surface area with respect to capital H. But here we taken the term with respect to capital D. And why I am writing for minimum surface area, this is the criteria. Means this is the mathematics, we have to use the derivative of surface area with respect to capital D. Then we can get the minimum surface area. Then guys, I hope you know why we require the minimum surface area. Why we require minimum surface area, you know already, correct? Minimum surface area means minimum surface area for heat transfer must be there. And in here you can see that the d by dd of surface area, that is pi by 4 d square plus 4v divided by d is equal to 0. Therefore here pi by 4 derivative of d square is 2d. And here 4v by d, it is 1 by d, that is minus 1 by d square is equal to 0. Okay, and then here I am writing pi by 4 into 2d is equal to 4 by d square. Volume is pi by 4 d square h. This is the volume. This is the volume. And see here which terms, this pi by 4, this pi by 4 get cancelled. Then how many terms are going to cancel here? This d square is also going to cancel. Then here 2d is equal to 4h. Therefore, height is equal to diameter by here the, then here 1, here it is 2. Then diameter is equal to 2h. Then height is equal to what? Diameter by 2. Height is equal to diameter by 2. This is the final answer. This is for top riser. Here I am writing for top riser. For top riser. Okay, for top riser, the height is equal to what? The diameter by 2. This is the relation. Means for the top riser, if we are taking the height is equal to diameter by 2, height is equal to diameter by 2, then what happen guys? The minimum surface area for heat transfer we can get. The minimum surface area for heat transfer we can get, therefore we can maintain the molten metal for more time. We can maintain the molten metal for more time. Okay. Then riser can supply the molten metal to the casting cavity. Now guys, discuss the condition for side riser here. Okay, side riser. And the volume is equal to pi by 4 d square h, same. H is equal to 4v by pi d square. H is equal to 4v divided by pi d square. Then here the surface area we have to write for the heat transfer. What is the surface area for side riser? Okay, the top is transferring heat, the bottom is also transferring heat, and this curved area is also transferring heat. You can say that this small area is not transferring heat, but we are neglecting. But actually this case is there. Top is also transferring heat, this we are considering as the bottom. This also bottom is also transferring heat. In that curved area, this small area, this one and this small area is not transferring heat, but it is very small, therefore we are neglecting. The same way we are neglecting here. Okay. Then top is also transferring heat, bottom is also transferring heat, and curved area is also transferring heat. Therefore, I am writing here the surface area transferring heat is equal to top area is pi by 4 d square, the bottom is pi by 4 d square, therefore it is 2 into pi by 4 d square plus of guys the pi d h is here, and therefore 2 into pi by 4 d square plus pi d h is 4v divided by pi d square. Correct? Therefore, here see the pi get cancelled, this get cancelled, and therefore here the surface area is equal to pi by 2 into d square plus 4v by d. 4v by d, volume is what? Pi by 4 d square h. Okay. Or no need to put the volume here, no need to put the volume, just wait for that volume. Okay. Just wait, only the volume I am going to write 4v by d. Okay. Pi by 2 d square plus 4v divided by d. Okay. Now guys, for minimum surface area we have to take the derivative here. Then here I am writing the derivative of surface area with respect to capital D is equal to 0. Therefore, derivative of surface area with respect to capital D, the surface area here it is pi by 2 d square plus 4v by d is equal to 0. Okay. Then here the d square, derivative of d square is 2d. then here it is pi by 2 derivative of d square is 2d plus 4v by d square, then 1 by d, derivative of 1 by d is minus 1 by d square, then it is 4 into volume is pi by 4 d square h, this is the volume of riser, is equal to 0. You see how many terms are going to cancel here? Guys, this d square going to cancel, this pi going to cancel, this 2 going to cancel, this 4 going to cancel, then you can see the d minus h is equal to 0 here, d minus h is equal to 0, d minus h is equal to 0, therefore h is equal to d. Therefore, h is equal to d, and guys, this h is equal to d I am writing for side riser. H is equal to d for side riser. Okay. And here h is equal to d by 2 for top riser. Yeah, that guys, the two relations are important here, guys. The two relations are important, which we completed. Okay. Now here we have to discuss the methods of riser design now. Yes, now see the methods of riser design. Okay, methods of riser design. In that methods of riser design, the first method is Keynes method. Keynes method. Also, we can say that the Keynes method of riser design. Also, we can say the Keynes method of riser design. Okay, guys, here now two types of modulus are going to come in the picture. First, for solidification, we written that tau is directly proportional to m square. Then, guys, this capital M was modulus for casting cavity, and now this solidification time is for solidification time of casting. Now I am writing here the tau r is directly proportional to the mr square. Then here what is the tau r? Solidification time of molten metal in riser, and here what is the mr? Mr is modulus of riser. Then guys, here the two type of modulus and two type of solidification time are there. One is this tau is solidification time of casting, and this tau r is the solidification time for molten metal in the riser. In same way, the two modulus are also available. One is the modulus of casting, and second is the modulus of riser. And guys, this freezing ratio, this Keynes method is depend on freezing ratio, and I am writing here the freezing ratio. That freezing ratio is denoted by this x is equal to, guys, the freezing ratio means it is the ratio of modulus here. Then I am writing here, this is the modulus of riser divided by modulus of casting cavity, and guys, this is, I am writing as the equation 1. Okay. Then this is the freezing ratio, one formula, that is the ratio of modulus of riser divided by modulus of casting cavity. The next is, again we have the second formula for freezing ratio, that is x is equal to A divided by y minus b plus of c, equation 2. Now here there is big question whether to use the minus or plus. Okay, there is no numerical on that in the exam, and guys, most of the places we are going to use the plus sign only, but even though someone is going to use the minus sign, because some people believe that in the minus sign the no change in answer, but guys, always go with here plus sign, the plus is more correct as compared to minus. These values are ABC are very small, therefore either plus or minus there will be no change in the answer, therefore no need to worry, but to go with the plus. Plus is more right. A divided by y minus b, here the plus of c we have to use. Okay, guys, here now what is that capital MR? Capital MR is the modulus of riser. What is the MC? The modulus of casting cavity. What are that A, B and C? What are that ABC? A comma B and C. That guys, that all ABC are the constants. Constants. Then what is the Y here, guys? Y is volumetric ratio. Okay, Y is volumetric ratio. This Y is what? The volumetric ratio here. Then here the Y is volumetric ratio means, guys, what? The volumetric ratio means it is the ratio of volumes. Then guys, that Y is the ratio of volumes means this Y is equal to volume of riser divided by volume of casting. Volume of riser divided by volume of casting, it is the ratio of volumes. Okay. Then now next, guys, we have to put the equation 1 and 2. Now here the equation 1 is MR by MC MR by MC is equal to A divided by Y minus B plus of C. This is the equation, guys. We are going to equate that both equation. Now guys, here this is the Keynes method, and what I said that this is the methods of riser design, and there are total, guys, the 4 methods of riser design. Now you are going to learn the first method here, the Keynes method. Okay, you are going to learn the first method here, the Keynes method, guys. Okay, then guys, here the Keynes method first you are going to learn. In riser design means we have to calculate the dimensions of riser, we have to calculate the diameter of riser, we have to calculate the height of riser. Okay, then how to calculate from this equation the diameter and height? This is very big question. Then guys, the modulus of riser. In the today's lecture, I didn't write the modulus of riser, the standard values, but standard value for modulus of riser is d by 6, d by 6. And how we can calculate the modulus of riser? Guys, you tell me how we can calculate the modulus of casting. Modulus is volume by surface area. The same way the modulus of riser is also volume by surface area. But if we are going to calculate for the top cylindrical riser, means we are considering the cylindrical riser. We are considering the cylindrical riser, and guys, in the cylindrical riser, the two type, one is top riser, one is side riser. Either we are going with the top riser, or either we are going with the side riser, or in the some case we can use the spherical riser is there. Then in all the case, the modulus of riser is what? The diameter by 6. This modulus of riser is what? Diameter by 6. Therefore, I am writing here it is a diameter by 6 divided by modulus of casting, that I am writing the volume by surface area of casting. Okay, is equal to A divided by Y minus B plus of C. Then the values of ABC will be given. Why we have to calculate volume of riser by volume of casting? It is volumetric ratio. Simple ratio, volume of riser by volume of casting. Then here this V by S, volume of casting, surface area of casting is given. Volume of casting and surface area is not given. They are giving the dimension of casting, and from the dimension of casting we can calculate the volume of casting, as well as we can calculate the surface area of casting. Okay, then therefore we can get this term V by S, and finally here we will get the value of this diameter. This diameter we can get it here. Diameter. Okay, we will get the answer of diameter. But once we get the value of diameter, then it is not first we have to calculate the value of H also. How we can? Once we get the value of D, once we get value of diameter, once we get the value of diameter, then here we can get here, then we can write here h is equal to diameter by 2 for top riser, because we got diameter, na, put diameter here, calculate the h, and height is equal to diameter for side riser, and in that way we can get the value of both the diameter and height, and this method is known as Keynes method. Okay, guys, very interesting, very simple method here. The Keynes method here we completed. Keynes method here we completed. Okay. Guys, next is modulus method here. Then second method I am writing here, the modulus method. That is the second method of riser design here, the modulus method. Modulus method. Guys, the modulus method, now we are going to use the tau r here, means solidification time of molten metal in the riser. This is the tau r, solidification time of molten metal in the riser, and this is the tau c, solidification time of molten metal in casting cavity. Sir, listen carefully what I am going to tell. Okay. Then guys, here the tau r must be greater than, or in the worst case I can say equal to tau c. Tau r is what? Solidification time of molten metal in the riser. If the casting is going to convert into solid in 100 seconds, okay, then tau r must be 100 or more than 100, means 102, 105, 110. Otherwise, riser, if the solidification, if the casting is going to convert into solid in 100 seconds and riser is converting into solid in 90 seconds, then how the riser can supply molten metal to the casting cavity? Not possible. Then here I am writing the tau r must be greater than or equal to tau c. Okay. Then guys, here the tau r must be greater than or equal to tau c. Therefore, here we know that the tau is directly proportional to the m square. Therefore, tau r is directly proportional to the mr square and tau c is directly proportional to the mc square. Therefore, tau r is directly proportional to the mr square, then mr square must be greater than or equal to tau c is directly proportional to the mc square. Therefore, modulus of riser must be greater than or equal to modulus of casting. Then modulus of riser, we are saying it is the d by 6 must be greater than or equal to modulus of casting is what? Volume by surface area. Guys, modulus of riser is also there, volume by surface area, but if you are going to check our notes, then you will get how volume by surface area we got the answer d by 6, and that d by 6 is the standard case. Okay, that I written. But guys, here I need to do the one modification here. Instead of hurry here, I need to do the one modification here, guys. One modification I need to do. What is that modification? Guys, for safe design of riser, okay, for safe design of riser, guys, the MR modulus of riser. What is the safe design of riser, guys? Here the modulus of riser must be taken as 20% higher than modulus of casting cavity. Then modulus of riser, for safe design of riser, modulus of riser must be greater than 20% of modulus of casting cavity. And therefore, guys, I am writing here modulus of riser is equal to 1.2 into modulus of casting cavity. Then modulus of riser is d by 6 is equal to 1.2 into modulus of casting cavity. Therefore, this diameter is equal to 7.2 into modulus of casting cavity. Okay. and therefore here we can get the answer of diameter. And how to get the modulus of casting cavity? Volume by surface area. The casting dimensions will be given, then we can calculate. And once we get the value of D, then how we can get the value of H? H is equal to D by 2 for top riser and H is equal to D for side riser. Okay, and therefore here we can get the answer of D and we can get the answer of H. But guys, in the gate 21, gate 22, there was one question. The numerical or modulus method generally which I am taking in the class, they ask the multiple select question. Means what we think that only the theory multiple select question they can ask, but then ask numerical on that. Is by using this procedure we got the answer diameter, then one diameter we can get, but here we need to write one note here. We need to write one note here. Okay, what is mean by note here? Here diameter we taken the 7.2 into 1.3. Means here we taken here the MR is equal to 1.2 MC. Here we taken MR is equal to 1.2 MC, and here we got the diameter is equal to answer. But above diameter means this answer is not available in option, then what we have to do? If above diameter is not in option, then consider MR is equal to MC and then calculate the new diameter. Okay, and then calculate the new diameter. Understood? And in that question, the both options they given, multiple side question. By using this D also we have to calculate, and by using MR is equal to 1.2 MC we have to calculate, and by using MR is equal to MC also we have to calculate, and both answer was available. And this is the wonderful method here we completed, that is modulus method of riser design. Okay. Now guys, next is third method of riser design here, novel research method. Yes guys, this is the novel research method of riser design. Novel research method is, guys, in the world at different places the different methods are developed, and that all the methods, the all important methods which the world is going to use, that methods we are going to study here. And then therefore we are going to study the four methods. Now see the third method here, the novel research method. Guys, this method is depend on shape factor of casting. Shape factor. Then here the shape factor is equal to L plus W divided by T. Okay, what is the L here? Length of casting. And W, width of casting. Small t, thickness of casting. Okay, this is the shape factor, and according to that shape factor, means according to the shape of the casting we can calculate the values. Next here, the value of volumetric ratio here. Y volumetric ratio is equal to volume of riser divided by volume of casting is the volumetric ratio. Volumetric ratio is what? Here the volume of riser divided by volume of casting. Therefore, guys, here you can see the volume of riser is equal to Y into volume of casting. Volume of riser is equal to Y into volume of casting. Then here the volume of riser is, I am writing here the pi by 4 d square h is equal to Y into volume of casting. Okay. Then guys, what we have to calculate here, the volume of casting will be given, then this Y, how to get the Y, and when we volume of casting means they are giving the dimension of casting, then we can get the volume of casting. Then next is Y, how to get that Y. Once we get the Y, then if it is a side riser, then H is equal to D we can put. If it is top riser here, H is equal to D by 2, then it will be the pi by 4 D cube by 2 is equal to Y into Vc. Then here we need to get the value of Y. Okay, how we can get the value of Y here? Yeah, for that guys, one table is there. Shift factor, you can see for the one table is there. In the table, you see the value of shift factor is given, and here the value of Y is given, and here the shift factor and here the Y. Shift factor means here they are giving the dimension of casting, and according to that we can calculate the shift factor, and that shift factor values we can check. That shift factor value we can check here, and according to that we can select the value of Y. Okay, the corresponding value of Y we can take and we can put it here, and from that we can get the value of D and H. Okay, but where we can get that value, the shape factor values we can get from the design data book. Okay, then guys, we can get here the all values. In here we can calculate the value of D and H. Okay, then according to top riser or side riser, if it is a top riser, then we can put here the height is equal to D by 2, then it will be the pi by 4 D cube by 2. If it is a side riser, then we can put the H is equal to D, therefore pi by 4 D cube is equal to Y into Vc, then we can get the value of D and H, and this method is guys the novel research method of riser design. Now the very interesting method, the fourth method, I am going to write here the fourth method, shrinkage volume consideration method. Shrinkage volume consideration method. Shrinkage volume consideration method. Okay. Now in the shrinkage volume consideration method, you can see that here the Vc is most important, which is given in the numerical. Volume of casting. Volume of casting. Next, Vsc is the shrinkage volume. Small a is percentage of shrinkage. Okay, Vc volume of casting, then Vsc shrinkage volume. Shrinkage volume, just see, I am telling one example here. If the volume of casting is 100, and you can see that the shrinkage is 5 millimeter cube, then this shrinkage volume is 5 millimeter cube. Then this shrinkage volume is 5 millimeter cube. Understood how the shrinkage volume? Then guys, it is the percentage of shrinkage. Means if the percentage of shrinkage is 5%, then what I am doing, the 5% into Vc I am doing. Means 100 into 5%. 5% means what? 5 by 100. Then what is answer? 5. Then what is the formula for here shrinkage volume? Shrinkage volume is equal to, guys, here the small a by 100. Means it is the small a is the percentage of shrinkage into volume of casting. Therefore, we can get the Vsc, we can get here the shrinkage volume, we can get here shrinkage volume. Now next is what is the riser volume. Okay, just see here the shrinkage volume is 5 millimeter cube, then riser need to supply, listen carefully, then riser need to supply the 5 millimeter cube of molten metal, then what the value of riser? Then guys here the riser volume must be greater or equal to 3 times VSC. Now guys, why I am not writing the riser volume is equal to VC? Means guys, VSC, riser volume is equal to VSC. Why I am not writing? VSC is 5 millimeter cube. Then riser need to supply only 5 millimeter cube. Then why I am taking the volume of riser is greater? 3 times of VSC, greater than or equal to 3 times of VSC means what? At least we have to use the riser 15 millimeter cube. Why it so? Because guys, the some molten metal is converting into solid in the riser also. Therefore, here the big quantity of molten metal, big volume of molten metal for the riser we have to select. And what is the volume formula? Pi by 4 d square h must be greater than or equal to 3 times VSC. And then here you can see that we can get the value of diameter as well as we can get the value of h here. We can get the value of diameter as well as we can get the value of h here. Okay, but guys, here we can get the value of d and h, and many people are saying that here the method is over, shrinkage volume consideration method, but no, here this method is not over. We need to go with the checking. We have to check here, and for the checking we have the two cases. I am writing here the case 1. We can write here the case 1. Okay, then guys, here the two cases we have to study. Then what is the case 1 here? Case 1 is tau r must be greater than or equal to tau c. What is mean by tau r? Solidification time of molten metal in the riser must be greater than or equal to solidification time of molten metal in the casting, that you know already. Therefore, we are writing here the mr square must be greater than or equal to mc square. Therefore, I am writing the mr must be greater than or equal to mc. Then mr is d by 6 must be greater than or equal to modulus of casting, means volume by surface area of casting. Therefore, guys, where is the d here? D is here. This is the d. Now, we have to put the d by 6, and volume by surface area for the casting you have to calculate. And therefore, guys, here the LHS term must be greater than or equal to RHS. Okay, and if it is satisfying, then D is the correct answer. If it is satisfying, then D is the correct answer. Then if LHS is greater than RHS, then we got here correct answer. Therefore, if it is satisfied, then D and H taken as final dimensions. Then D and H taken as final dimensions. Then D and H taken as final dimensions. Okay, but now the question here, if it is not going to satisfy, then what happens? If LHS is not greater than or equal to RHS, the D by 6 is not greater than or equal to volume by surface area of casting, then what happens, guys? Okay, then what is the solution you have if it is not going to satisfy? Then same I am writing here, the tau r the same I am going to write here, the tau r must be greater than or equal to tau c. Then mr square must be greater than or equal to mc square. Then mr must be greater than or equal to mc. Therefore, here instead of d I am writing the d dash by 6 is greater than or equal to modulus of casting, then d dash is equal to 6 into modulus of casting. I am taking the d dash is equal to 6 into modulus of casting we are taking, okay, and we are calculating the dimension of d dash. Then here the d dash is equal to question mark and h dash is equal to question mark. These are the final answer. The d dash and h dash are the final dimensions, okay. D dash h dash means when we have to take this d, first here we are going to obtain this d, and the d value we have to check it here, we have to put it here and we have to check LHS and RHS. If it is not satisfying, then finally this d dash is equal to 6 MC and we can give the answer. Now here the last topic of casting chapter, we have to see it here, the G factor. G factor guys, G factor. G factor. Guys, in the centrifugal casting, to solve the numericals, that G factor is very important, and the G factor term is mentioned in rarely, very few reference book, or almost if you are going to check in the reference book, it is very difficult to obtain the G factor here. It is very difficult to obtain the G factor. It is not available. Then what is the G factor, guys? The centrifugal force here of molten metal, or centrifugal force is going to generate on molten metal to the weight of molten metal. Centrifugal force on molten metal. Centrifugal force on molten metal to the weight of molten metal. Okay. Then here I am writing this G is equal to centrifugal force is equal to mass into acceleration, and weight of molten metal is mass into gravitational acceleration. This m is mass of molten metal, this small e is the acceleration of molten metal, because the mold is going to rotate continuously, and in that rotated mold we are going to pour the molten metal. Therefore, the molten metal is going to accelerate here. This small e is the acceleration of molten metal, and therefore guys, here the this we are going to cancel, and we can write small a acceleration is equal to capital G into this gravitational acceleration. Okay, this is the acceleration of molten metal is equal to gravity factor into gravitational acceleration, G factor into gravitational acceleration. Then here we can solve the numerical. Then this acceleration is equal to, we can put the formula. Okay, given that all the formulas here, well, V is equal to R into omega and that all, you can put the formula for A and you can solve the questions.